Okay, welcome back everyone. In this video, we're going to talk about the concept of weight and how it can be applied to universal gravity. So, we want to talk about why is our original equation for weight equals mg, only good for the surface of the Earth, and then what's the relationship between little g and the physical constants, the mass and the radius of the Earth. So, first of all, the weight of a body is the total gravitational force exerted on that body by all other objects in the universe. That's the actual definition of weight. However, most of the time we just pretend like for objects close to the Earth's surface that everything else in the universe is so far away that it doesn't have much effect compared to the Earth. So that's because of that 1 over r squared term. And in this equation for weight, otherwise known as the force of gravity, ME and RE refer to the mass and the radius of the Earth. Okay? So the weight is the total gravitational force, and the gravitational force is G m1 m2 over r squared. So one way to think about this is that if we have the Earth, which is ME, and you have a little object m sitting on the surface, it's a distance re away from the center of the Earth. Remember that we have to calculate center to center distance. So this is the correct equation for the weight of an object. But we also know that weight is equal to mg for any object of mass m close to the surface of the Earth. So what we can do is we can calculate acceleration from the force of gravity divided by the object's mass, little m, which is weight divided by little m. And so what we find is that since weight is the force of gravity, which is g mm over r squared, if we divide that by m, then what we end up with is an acceleration of g, mass of the Earth, over radius of the Earth squared. And we know that at the Earth's surface that has a special name. That is little g, which is 9.8 meters per second squared. Or maybe another way to look at it is to look at the fact that this is force divided by mass, and to recognize that this is also newtons per kilogram. So we'll come back to this thought in a moment, but this value of g could have units of newtons per kilogram. In other words, every kilogram of mass which is sitting on the Earth's surface experiences 9.8 newtons of gravitational force or weight. And that brings us to the fact that we can plug in the mass of the Earth and the radius of the Earth, and we're going to get 9.8. So I invite you to try this to satisfy yourself that this really does occur. Okay, now the gravitational field is this value of g that we found in the previous slide. And notice that if you multiply this by a little m, you're going to get the weight, which is the gravitational force. Okay, so g, which is 9.8 meters per second squared, or 9.8 newtons per kilogram, that's our value of the gravitational field. And, whoops, I wrote over here, this is the definition of the gravitational field. It is defined as the gravitational force per unit mass. So the gravitational force per unit mass. And that's newtons per kilogram, right? Which is exactly what we said here. Now this is going to be important later on when we study electric fields, because electric field will be a force per unit charge. So it'll be kind of the same concept. Okay? So this is gravitational force per unit mass in newtons per kilogram. So one thing that's kind of confusing about this is that we can think about g, the gravitational field, as a couple of things. It can be the value of the gravitational field at one point. In other words, we have a function, okay, g of x, y, and z. which is a vector valued function, which says that if you go somewhere, you're going to have a value of g, which depends on your location, your xyz coordinates, or g could also be a collection or a map of a lot of field vectors. So what we mean by that is we could draw the Earth, so ME, and we could imagine putting a small m in lots of different places and drawing the force on that small m. Okay, that would be a test mass. And we call this a test mass because m is much, much smaller than the mass of the Earth, so it's not really affecting the Earth itself. Okay, and if you go further away, you have less field, and if you go closer, you have more. Okay, so the thing that's confusing is that little g can be the value at one specific point in space, or it can refer to a collection of these field vectors. So we just have to be careful. Okay, and we can take a look at this applet here, loading up. Okay, and if I change this to field vectors, here is another way of viewing the gravitational field of the Earth. Okay, so the brighter the arrow, that's going to tell you sort of how strong that field is. And notice that they all are pointing inwards. So this is a 3D thing, and I like spinning it. It's kind of fun. Okay, so in any case, that's what the gravitational field is. Now, when we talk about weight, this is something that's going to decrease with distance from the Earth's surface. So the weight is gmm over r squared. Okay, and r is the astronaut's distance from the center of the Earth, but the distance from the surface of the Earth would be r minus the radius of the Earth. Okay, and we could call that the height. Okay, so let's do an example problem. So we have 4 new planets that we discover with radii and masses as listed here. We want to rank them in terms of the value of g at their surface, from largest to smallest. So we recall that g is equal to big G, big M, over r squared. And if we look at this, so Altair is basically going to be 2/4 times what we have on Earth. Betelgeuse, or Betelgeuse if you want, is going to be 4/16. Okay. Canopus is going to be 4/4, which is 1, and Deneb is going to be 2/16. So that means that our largest value of g will be Canopus, because it's the same as us, and then next will be Altair, and next will be Betelgeuse, and then Deneb. Now, as I'm making this video, actually in the news recently was a very close solar system. I think it was the TRAPPIST system, which has, I believe, 7 planets that are orbiting very close to their star. So we can sort of use this information, if we know the mass and the radius of these planets, to determine how Earth-like they are. Okay, so next time we're going to talk about gravitational potential energy and how it is a little bit different than what we did back in our energy unit.